Well, the microphone wasn't on yet. Okay, but it is now. Okay, so I'm just going to roll right into my lecture. I'll talk about a number of different things, pick up on some of the topics that you've already heard. But first of all, I wanted to thank Professor Gupta and Professor Kulkarni and the organizers of this GIAN project. I think it's very valuable and useful to have a more in-depth interaction with people. I've done that once before. I did a sabbatical leave in 2008. Professor Kulkarni was my host down in Bangalore at JNCASR. And having more sustained interactions is much different than seeing somebody in a 15-minute talk at a conference. So hopefully we can get to know each other and interact with some depth. Also, I would be remiss if I didn't mention the folks listed here who have helped develop this topic with me. My graduate students and postdocs, faculty collaborators are listed there, and the financial support of the GIAN program and other entities in the U.S. that have supported the work that I'll describe. So I'm going to give a brief motivation, and then we'll quickly go into some general deposition methods. I'm just going to kind of fill in the gaps for some topics that weren't covered in depth already by the previous speakers, and then I'll finally move to carbon nanostructures, which is an area of research in my group. So the first type of motivation I want to give relates to what is the central topic of this short course, which is energy storage, and in particular supercapacitors. We'll talk much more about supercapacitors as the week goes by, but just to kind of show this slide, this was a market survey from about a year ago, and the idea, the projection, and this is a business projection, is that supercapacitors could replace up to 50% of the lithium-ion battery market today. And that's a huge market already, right? So you could imagine, what's coming and what it's going to take to get there. I don't want you to read all the words on the slide. You'll have access to these slides later. I want you to see, however, that when you do a cost breakdown of a supercapacitor, the electrode material accounts for half of the cost. And one of the reasons that supercapacitors have not surpassed batteries yet is that they are more costly in general. And so one of the things that we should talk about is we want to make really good electrode materials, but as the previous speaker mentioned, they also have to be cost effective. Otherwise, people won't use them. So that's I think a subject for later in the week as we look at some of the details of those materials in the context of supercapacitors. But I wanted to put that out for you to understand that when we talk about structuring materials, many times it's not just about what it looks like at the end, it's also how did you get there, and is it cost effective, is it non-toxic, is it environmentally benign. I also wanted to just introduce a very, very simple schematic of a electric double layer capacitor. It's shown here. In this case, you have two electrodes, the charge collectors on the top and bottom. You have some kind of active layer of material potentially, and you have an electrolyte in which charge can flow, and then it piles up at the interface between the electrolyte itself and the electrode. Now, in the case of a double layer capacitor, what happens is that these charges, once they separate, they will move in opposite directions, positive up in this case and negative down, and they will attract the opposite charge in the electrode, and that's what makes the double layer. And if you think about a double layer, an individual double layer as a capacitor itself, then really this, what we would look at macroscopically as one capacitor, is really two. It's really two capacitors in series. And capacitors, when they're in series, they add like a resistor does in parallel, right? So you lose capacitance by that, which, but this is the general structure. And just moving a little bit deeper to motivate, again, material synthesis, I wanted to show why it's important to have surface structure that gives you high area. So if you understand that charge accumulates on a surface and that produces capacitance, and you want the highest capacitance possible, then you also will want the highest area possible. And that's why three-dimensional materials are important for this subject. It's also true for batteries. But I would just highlight the fact that if we can have, the more surface area we can have, the more charge we can store. There are other factors that will come into it, and we'll talk about it throughout the week. It's not just about surface area. You have to be able to access that surface area. But to first order, as a scientist or engineer, if you want to make a system of materials have higher capacitance, the first thing you should do is increase the surface area, right? It's the easiest in general to do. Now I'm going to take a deviation here a little bit and talk about some deposition processes, because on top of those surfaces, in many cases, and we'll learn more about this later in the week, we'll actually want to put a coating of something on those surfaces. And so I want to talk a little bit about deposition processes. And in doing so, there's a nice set of slides and some lectures by Mark Maddow at UC Irvine. And so I've taken a few of those as examples and overview slides, because I think that they're very helpful and they summarize the topic quite well. In general, we have two kinds of vapor deposition processes. One is physical vapor deposition. You've heard about that to some extent today. And the other is chemical vapor deposition. You've also heard about that. I'm just going to kind of fill in the gaps of some of the other processes that were not covered earlier today. And so physical vapor deposition process is it's a strange name. I always found it to be strange because I'm not sure what the physical is supposed to be, right? I think what it really is intended to mean is that there's no reaction that's going on, and so you're kind of physically throwing your material onto a substrate. So what happens in physical vapor deposition, you have, in general, you make a vapor, and whatever is in the vapor, that is what ends up on the surface, as opposed to a vapor that's formed that might react along the way to reaching the other surface. So physical vapor deposition processes, in general, come in two forms. At least the two most common forms are electron beam evaporation and then thermal evaporation. In the electron beam evaporation, you're essentially using an electron beam to heat a source and vaporize it. And you can do that with high precision, and you can do it very locally. That's why you use the electron beam. For thermal evaporation, instead of using an electron beam, you essentially use a heater, and you heat up a larger area of that material, and then that evaporates out in vacuum. And there's some principles that you have to follow. When you're looking at thermal evaporation, for example, you can do some quick calculations for how many molecules that will leave a surface per unit area, per unit time. And the temperature is important, so if you make it hotter, you'll get more of these things out. Phi is an energy term. It's like a work function for electrons, but in this case it's for ions, or for molecules and atoms that come out. But what you really have to do, if you design a chamber, when you're designing an evaporation chamber, you have to design it so that your mean free path, that's the average distance that an atom or molecule will travel, that path is longer than the distance between your target, which would be down here, and your source. Okay, so that's the general idea. You want to make sure that whatever you're evaporating does not undergo a lot of scattering events along the way, because then it will start to go in places that you don't want it to go. This is another way of looking at it. In general, you'll have your deposition surface, you have your evaporator. You'll do some things with your evaporator. You try in physical vapor deposition processes, you try to make it line of sight. Again, if your mean free path is longer than the distance that separates your target and your deposition surface, then you can get line of sight. You can get straight-walled types of deposition processes. So one of the things that you want to be able to do is you'd say that you'd want to have this is a Knudsen number, the Kn term here. That's the mean free path divided by d, where d is the orifice diameter of your evaporator container. And then another important factor here is that you have an exponential type of term that tells you what fraction of the particles that are emitted from the surface would undergo scattering events. So d, the lowercase d here, is the distance between your target and your deposition surface. And again, the mean free path is central to all of these things. How do you control the mean free path? Well, it's pretty simple. You drop the pressure. You have as low a pressure as possible, and that's why in practice, e-beam evaporators, thermal evaporators, the thing that's the most important to maintain, and also the thing that breaks the most, is the pump. Right, the pumping system, the vacuum pumping system, is central to those processes. Now, a similar type of deposition process is called sputtering. In this case, what you do is you create a plasma. So it's not a pure vacuum, or it's a higher pressure environment typically than what you'd have for thermal evaporation or e-beam evaporation. You ionize a gas and then accelerate that to a surface of your target. And so instead of having an evaporation event from your target, you have essentially an ablation type event where ions are bombarding the surface. To some extent, you can control the energy of those ions by controlling the